Limited and methodAI extend a very warm welcome to the participants of today's AI webinar. It feels nice to have you all here and we thank you for that. A bit about the House of Sultan first. Pioneers in the field of book publishing in post-independence India, we cater to students from pre-primary to university level, churning out over 600 titles, besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the nation as well as in some neighboring countries. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce you to the host of today's webinar, Dr. Sachin Gupta. Besides authoring artificial intelligence and data science textbooks for classes 9th and 10th, Dr. Gupta is Dean, Research and Innovation, Maharaja Agrawal Institute of Technology, Guru Gobind Singh Indraprastha University, Delhi. It gives us immense pleasure to inform you that Dr. Gupta's latest book, Decoding Artificial Intelligence, has won the Outstanding Contribution to AI Literature Award recently. A great achievement indeed. Besides, Dr. Gupta has also been HOD Computer Science Engineering and MCA Department, Dronacharya Group of Institutions, Deputy Director and Head, Computer Science Department, Chandraprabhu Jain College of Higher Studies, affiliated to GGSIPU, Delhi. With a teaching experience of over 20 years, which includes teaching undergraduate students, graduate students, and postgraduate students, besides researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIPU. Dr. Gupta has also contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are truly commendable. May I now request the host of today's webinar to take you through the session, Dr. Sachin Gupta. Have a great day ahead. Thank you.
Thank you so much, sir. Thank you for having me. Thank you for everyone who has joined the session today. I could have started a bit earlier, but I was traveling. I just came in. So this session is in continuation with what we covered last session, that what are the challenges of computer vision. And we are going to practically see how computer vision works today with two models, one being rule-based and the other being machine learning based, so that you'd be able to distinguish very clearly that what are the different operations that computer vision performs usually. With the last class, several people who were joined, they said that we want to see how practically computer vision goes into working. So that is what I am going to try and share with you. Please feel free to send any query that you may have on the chat window whenever you have one. I hope I am audible. My screen is visible.
Yes, everything is fine, Dr. Gupta.
Yes. So the environment we'll be using today is a cloud-based environment called Google Drive. And you can comfortably see Google Drive Collab. Collab on Google Drive is basically a platform which allows you two things into one. One is it has a computation environment. So just see that there are three things denoted here. One is this is connected to a Python compute engine. Secondly, it is providing me roughly 13 GB of RAM, out of which I am using 2.64 GB. And thirdly, it is also using 26 gigabytes of disk space that I would have to normally give it on my own. With image classification, this is usually a challenge, that how much data are we going to utilize. So you would always find the challenge being that how to reduce the size of the images that we are working with. What is a channel? Last time we discussed channels in detail, that there would be a RGB, and we are going to today work with a data set that is going to classify day and night images from a data set that is archive of many outdoor scenes. So this, if you search for archive of many outdoor scenes, this is a very huge database. But I have taken only roughly 100 odd images of both types of the something like image of day and some images of the night, for instance. So what do you prefer first, easy way or the hard way? Machine learning or without machine learning? That is what we are going to cover. The second thing that we are going to cover is a teachable machine. That how do you run computer vision on a cloud platform? This is again from Google, a teachable machine. Here you can have different types of data, that can be images, that can be audio, that can be pose projects. So we are going to work on a image project. Now, for everyone who worked last time, there are two models on teachable machine. That one is the best for most use cases. The images should be 224 cross 224 pixel. From the last session, you may recall that each pixel is a feature in an image, and we want to have standard size of images so that all of the images contribute equally to our model. This sometimes we want to generate for machines like mobile also, where the computation power is less. In that case, we might use images which are smaller and grayscale. That means we would work only on one channel and the image size should be smaller. So we'll work with a standard image model here. Right. This works as simple as this. That you would have a class 1, let me call it day images. You would have a class 2, let me call it night images. I may upload the samples from the file, or I may import them from the Google Drive. So on my drive, there are, you can see the images for day and night are available. For the day folder, let us select some images and add them to our classification machine. So you can see, I hope that works. Yes. So all the sample images, there are roughly 109 sample images that I could choose out of the day images. And I'll upload some from the night images again. No, not from my machine, but from the Google Drive. Similar manner, you just have to add. See how simple the machine learning is going to make it for you. You would not be writing any code, absolutely nil, and you would still be able to demonstrate computer vision to your students. This is the second step, that you have added the night images. Right. I train the model. This is happening on the browser itself. So it would give you a warning that you should not close your browser while this is training. And it is learning from the features of whatever images that we are providing to it. Now, our classification as day or night is our own. That the computer does not understand what do you mean by day, what do you mean by night. It is just going to take this set and going to take all of the features which are common to these. Again, this set all of the features which are common to these, and then put it into mathematical model, that what is it learning from them. So there are several options. You can actually place your images to check from a webcam. Let us open the webcam and try to take a picture. Okay, webcam permissions are not there. We'll take it from a file. Choose from the Google Drive again, and let us take in a different folder just for test. So for the image which I have selected, it was coming from the day data set, but it is posing as night because it could not be classified properly by the machine. In a similar fashion, if I am going to pick up another image, so there may be errors for everything that you may work with. From the training data, any image that you pick might be closer to what the model thinks it's a night, might be closer to what the model thinks it's a day, but with some predictability or some probability, it would say that this image is either day or night. So this says 100% sure that this is a day image. You can export your model, use it into different projects. That is again a possibility. But let's not go into that. Let's understand into what is happening behind the scenes here. Can somebody put in the chat window that what do you think would be the parameter on which they would be classified? What features? Based on human intelligence, that what do you think would be the feature on the basis of which this is going to classify it as these are the day images, what is common to the day, what is common to the night? Anybody for that? You can share in the chat. Okay, we started with easy. If the image is bright, it's a day image. Perfectly fine. Abha, thank you so much for having that thought that most of the time the machine is learning on the basis of brightness. But what constitutes brightness as far as our knowledge goes? That how would we describe brightness? That is the case of study. Yes, if it is dark, it would be a night image. Thank you so much for that input. Let us now work on a completely different approach to the same thing. I have mounted the same data set from my drive and imported the images on training and testing in two different directories. There are some libraries that I require. So matplotlib.images and matplotlib.pyplot, computer vision 2, random numpy for processing data. After storing these into the directory folders, I'll just try to load the data set. Now, I'll take you back to what we discussed earlier, that the images should be standard sized, that each image should be fixed size. What the model is going to convert them would be like teachable machine did it for 224 cross 224 pixels. It converted them automatically when we fed it to it. But for our classifier, we are not going to use any machine learning at all. And we are still going to be requiring that all the images are standard. So we load the data set from the image directory, which you have actually discussed here. Then you store all the list or the images list into data set. All the image types also can be stored with day or night. Then we iterate through each color folder. For every image, you read the file, and if the image is not available, sorry, if the image is correctly read in that case, we are simply appending it to the list. That's the pre-processing for all the images. We are going to call this function on day images also, on night images also later. So first is first, we create a list of images for the training data. This training data contains what? This image directory training contains the content of the training set. Training set is containing both day and night images. Okay. Then we pick up an image just like any index because we have already created a list. And from the index, you would have to select an image from the image list with the image index 0. And we show the selected image. Okay. We print the selected image and its shape, and you'd be able to see that the image is 471 pixel cross 640 pixels. And then the image has 3 color channels. So the shape of the images, it tells us that how many color channels are there. This being a RGB image, obviously it has 3 color channels. And finally, we see the label of the image is a day. Now I'll try for another image, that image index 192. This would be coming from the night data set. We again print the same properties, that from the list, pick up an image. Then for the selected image, show the image and print the image along with its channels, number of channels that we have. This is the property. So this image is 555 pixels, 800 pixels. That means the size of the two images is different. This image was 471 cross 640. This image is 555 cross 800. But the color channels are same. Both have red, green and blue, 3 channels. And the label of the image is night. So far we have just loaded the images. We saw the properties that the image can be printed. The image has a label. The image has 3 color channels. So far, so good. The next step in computer vision that we are going to do is we want to standardize the images to a same size. We want every image to be of the same size before we go on into training. So pre-processing, we resize every image to a standard size and then encode the target variables. I'll talk about the target variables soon. So for standardizing, what do? We take a cv2.resize function. This resize function allows us to change the dimensions of an image. So any image, whatever size it was, it would now be converted to the standard pixels that we are feeding. So we are converting every image that we have to 1100 cross 600 pixels. The smaller image would be converted to bigger. And this function is going to return the standard image with the same size. We'll call this function on every image. Secondly, what we need to do is, our target is, we want to classify the image as either day or night. We want a binary classifier. What the machine learning does was easy. We gave it 2 different labels and then we started training. After training, we could get a mathematical model and this would be able to predict. Abha said that this was happening because of the brightness. So far, we haven't spoken about the brightness here. We are just simply standardizing the image to same size. But we need to encode the label. If label is day, computer does not understand day. I have to convert it to a numerical value like 1. Otherwise, night would be classified as 0. So my images have the label of day image is 1, and the label for night image is 0. So we are just simply converting the text day into 1, night into 0. That's all that we are encoding so that the computer understands what the numeric value is. Now, after having these 2 things done, we call pre-process. So on the complete image list, you now want to create a new list which is standard after resizing them. For each image, what you do is you convert the label to the standard value. You call the function standardize on the image, encode the label, and finally append it to the standard list, that's the standardized images that we were trying to create. So once we have done it, our job is done. This function would be called across what? Across the 2 lists that we created, or sorry, the 1 list that we created for the normal images, which was non-standardized. It contained every image. For each image now, we are going to pick up the values of the image, standardize the size of the image, and encode the label as 0 or 1, as day or night that we were doing. So standardized list would be called on the image list that we created originally in the top. This was my image list, which I had loaded the complete training data set on. I call now the standardized function on this image list. Please ask, okay, I see some query. Yeah, Subhashini, I'll share the code and data set both. Don't worry. Any other queries so far? Okay, thank you. So what we have done so far is we have loaded the images. Then what we did, we observed samples loaded. We also saw the characteristics of the image, channels. Then we standardize for image size, and we encoded text labels into numerical labels. This is what we have done so far. Correct. Now what we want to do is we now want to check the brightness. Right. Before that, look at a standardized image as we did with the normal. So pick up an image, show the image, and show the shape. So for each image, the shape would be 600 cross 1100 pixels, and it has still got 3 channels. Right. We also show the label. So for the day images, one was day, night was 0, and the label of the corresponding image is 1. That means it's a day image. Similarly, you can check for the night images also. That would work. So if my image is 192, for instance, and I run this cell again, this is going to return the shape as 600 cross 1100 pixel. The image is standardized. The number of channels are 3, and the label is a 0, indicating this is a night image. All right. This is just for checking. Now we want to extract the features. So features in the case of computer vision, last time we discussed that pixel is the smallest unit of storage in a computer vision module, and collectively the pixels are adding to features which can be edges, which can be color, which can be density, which can be a texture, which can be, there can be a lot of things that we would worry about the features of an image. Abba said that brightness is the one feature which is actually a distinguishing factor, because day and night images have got one basic parameter which is different, which is called brightness. So we want to extract the average brightness here using HSV color space. Now, RGB talks about red, green, and blue. It does not talk about brightness. So computer vision allows us to convert a RGB space into a hue, saturation, and V. That is the measure of brightness. So we want to use the V channel, which is the measure of brightness, add up all the pixels, that what is the value of the V channel in a pixel. So each pixel would have a H value, a S value, and a V value. We want to extract the V value of the pixel, add all of them up, and then whatever sum we get, we are going to divide it by the area of the image. Okay. So dividing by the area of the image gives us what? That I had suppose 1000 pixels. Each pixel has its own V value, that was the brightness. I added all of them up, divided by the area of the image. So I get the average brightness per pixel for each image. I hope that is clear so far. We are going to do it in code again, right? So hue represents color, saturation is the grayness, and value represents the brightness. We want to work on the brightness part as of now. So to find the average value or brightness, what we do is, first thing, we convert the image to its HSV value. That we call a function from CV2, which is called CV2.color_RGB to HSV. This function takes in input an RGB image and returns of image which is HSV. Okay. Then HSV has got three parts. There is a part called hue, then saturation, and then value. So we want to add not the 0, not the 1 channel, but the second channel. The second channel is about brightness. We take sum of all pixels using np.sum, numpy library, and then we take the area of each image to be, because we converted the image to a 600 cross 1100 pixels. So naturally we can calculate the area as 600 into 1100 and then find the average brightness for the image, which would be sum of the brightness divided by the area. Okay. So the next step that we have done is calculate the individual, sorry, convert first. This is important because we want to have the brightness component extracted. Extract and add all V values using numpy, and then now when you work about the area of the image, had it not been standardized, now why is standardization important? If my images had different areas, some with a smaller area, some with a bigger area, then I would not be able to compare them. I want to be able to compare each image of the same area, of the same size, that what is the average brightness of this particular image as compared to the other. So unless and until I have a standard size of the images, I would not be able to compare them. So that is one big reason why you require to standardize all the images on the same size, because there is a comparison, there is a classification happening later. Now this part done, I would have to now test the different brightness levels. Let us take an image number 178. We are going to test the image by storing it into a variable, find the average brightness using the function average brightness, and print the average brightness. So average brightness for this image comes out to be 99.62 something. Use the same formula. We took all the pixels, took the sum of the V values and divided by the area. So for this specific image, the brightness comes out to be 99.62. Right. Let us say this image was 34 and we want to run the same test on it. So average brightness is 192. That means this image is far more brighter than the image which was 99. Right. So you can see the day images have got a higher average brightness as compared to the night images, which have a lower. So check it across another image, which is a night image, and the average brightness here is only 21. It's very dark. Okay. So the question to the audience is that I understand the average brightness I have calculated. What I want now is what is the value for the threshold that this brightness, above this brightness, we want everything to be day, below this brightness, everything should be night. What threshold value to use for classification? How are you going to decide? What is a good value? Like, should we use like 100? Should we use 90? Should we use 80? There is, what do you think should be a good threshold? Against which that इससे ज्यादा brightness है तो it's a day, इससे कम brightness है तो it's a night. This is human in the loop. This is Abba says 100. Why 100, Abba? So you saw that the average brightness for the one of the night images was 99. Subhashini says 90. Yes. See, this is something that human in a loop has to actually work on. we do what? We'll have to do a hit and trial. We'll try to see how many images are properly classified against 100, how many are misclassified against 100. If that misclassification is high, then we reduce the threshold to 90. If 100 is classifying good enough, fair tolerance, we will use 100. But we can actually working on this. So this is again what we do in the next step. We build a classifier with an estimate label for a threshold. This threshold is something that we are going to define. That here the threshold is 100. Okay. So if I have taken a threshold of 100, in that case, if the average is greater than threshold, we predict the label to be 1. That means it's a day. If the threshold is less than if the average is less than threshold, we predict the label to be 0. That means we classify the image as a day or night based on the threshold value. So for each image, you extract the average brightness and compare it with the threshold value. These are the only two things that we are doing here. Fine. Then machine learning does what? It keeps on iterating between different values to reach a specific evaluated. That means you do MAE, you do MSE, you do a lot of model evaluation, which allow you to see that whether my training data is as good as, or what the model is working on training, would it work also on test data? Would it be able to generalize? Would it be able to classify the images that are not seen? So how do we evaluate? We load the data set for the testing directory now in the test image list, pre-process them to convert them to the same size, randomly shuffle them, right? And then start classifying, comparing the test images with the threshold. Now, we already know the test images have got a label. It's a day or a night. If it is classifying a day image as a day image, good. If it is classifying a night image as a day image, that is bad. So we want to see how many times it is classifying a day as a day and a night as a night. If the number of misclassified images is high, then our threshold is not good. If the number of misclassified image labels is less, then our threshold is good enough. So you iterate through all the test images. You get the true data. True data is what is stored in the label of the image. You also get the predicted label by calling the estimate function on the test image. Compare that the true label which we already had and the predicted label which we are comparing with the threshold, are they equal or not? If they are not equal, the image is misclassified, and we store it into a misclassified image label. Correct? I hope so far is okay. And then you call the function for all the misclassified images. After you get the misclassified images, you do an accuracy calculation, that how many images were there in total, how many numbers were correctly identified, that is total minus misclassified images, and the accuracy would be number of correct images divided by the total. That's all. This is all human. We have not done anything which is automated. Every process that we have done is by hand. We use computer vision libraries for standardizing, for RGB to HSV, but that is all that we are doing here. So, and then we finally calculate the accuracy, we print it. So accuracy of our model is 93% here. That means only 11 images out of 160 have been misclassified by our model. This is fairly good. With the threshold of 100, this worked very fine. So if we can change the threshold to 90, and if we see the misclassified images going up, so we can try it with different values, 100, 101, 102, 103, and so far. And then you can import a confusion matrix to generate true positives, true negatives, false positive, and false negative. So you can see the true negatives are 72, the true positives are 77, but there is a false positive which are more and false negatives which are less. So you can create a classification matrix as it would be done by machine learning also. You can find out the precision, recall, and accuracy and F1 score, all of them. So with a good recall of 96%, with a good precision of 90%, with a good accuracy of 93, my model is perfectly Fine. The only problem is that there is no ML completely. So we received an accuracy of 93.75 by using only one single feature extraction. We haven't talked about that there may be more features which might give me more accuracy. So by single feature, we could work on this. Compared to this, the technique was harder, but this is giving you an essential idea into what a usual machine learning algorithm works in the background, that it would take the image, extract some feature, that may be brightness, that may be some more other features also, and then try to make a prediction based on comparing the threshold with the features that it has extracted and then possibly classifying. Exactly this goes on into computer vision, but if we are working on one single feature, it was possible to do it by hand. If the images are complex, it would not be possible for us. So there comes in CNNs or convolutional neural network, where you actually extract all the features, then uh, use those features to build a model, sometimes into deep learning domain, and eventually then you try to classify whatever task or predict whatever task that you were trying to do. So I hope that gives you a very fair idea about how challenging computer vision is. See, this is a small image, this is a small data set which we are trying to classify. It takes a lot of RAM, a lot of disk space also. So think about the models which are working in a huge image space, like satellite images. They are very big in size. How do we work about predicting weather patterns from them, or predicting agricultural produce from images of a area of a satellite? So those are the things which anybody who is working into computer vision should understand, that images tend to be big. We have to reduce the channels sometimes, we have to reduce the size sometimes, we have to sometimes even leave out some features which are unimportant. But at the end of the day, if your model is going to take a lot of images, you have to shrink those images by removing some features which are non-essential. Right. I'll open the floor for anything, any query that you have related to whatever we have learned, or it may be beyond about computer vision. So that please ask me any question that you have, and I'll download this file and share with uh, the group here. So data set you will be able to search as AMOS, archive of many outdoor images, and the classifier, the complete model I have already shared on the chat window with you, so that you can download it before we close the meeting. In the meanwhile, okay, right. So Abha says, so the robots which are using AI like Sophia must have all large memory into it. Sophia, there are two things. There are two things, Abha, that come. I'll share in the group for sure. Uh, I guess there is a WhatsApp group. Ashish sir, can you please share the link to join the group, if in case it is feasible, so that they can add in their doubts. Okay, coming to question of Abha. Abha, so long as I was computing, just check out that till the time I was computing the teachable machine, till the time I did not have a model trained, till the time I needed every image sample to be stored, for sure. But once I have this thing, the model actually, this is basically a mathematical model. So if I download the model, right, and I save it in p5.js or JavaScript or a pickle file, in that case, the actual uh, application like Sophia like self-driving cars, they get to store not only the complete imagery, instead they store the model. So once I have trained a machine enough to understand all the roads, what are the possibilities, what are the road signs, what are the dividing signs, what a human looks like, what a car looks like, that becomes a model. So the robots or the self-driving cars, they actually get to use the model which has been pre-trained. So the concept which we use in machine learning is called pre-trained model. So I might be using somebody else's model for training day and night images. So if somebody wants to actually classify day and night images and I have already trained a model, they can just simply import the model, give it an image, and the image would be immediately able to classify. They don't have to use the data set, they don't have to use the training, they don't have to use anything. They pick up the pre-trained model, feed it an image, and it would be immediately given output. I hope that answers your query. So that is pre-trained. And you can use pre-trained model as well. So whenever you are using anything in machine learning which uses a pre-trained model, you'd be using the same phenomena, that you don't have to train the data by yourself. You have a chat also. I'm going to share my LinkedIn as well. Yes, the importing libraries is libraries need to be compiled. They are added to your code. Models are ready to use. They have learned it, but all depends on what the model has been trained on. It would be able to do only that task. Libraries can be put to use to several different alternate tasks as well. Please ask me any more question that you need to. I'll just add in my LinkedIn profile in addition, so that you can connect and you can share the queries as well on LinkedIn also. Subhashini, I hope you have joined the group. It's a group for faculty members where we discuss a lot of things that are about artificial intelligence. My system is overloaded with data. Okay, I would have to Zoom. I have to keep. So I hope I am still audible and visible
Yes, you are.
on LinkedIn, and you would be able to find out for sure. Any more questions, please, before we wind up? I have shared the code. You can do it with any sort of data set which you want to procure. This would work with all of them. Store the drives, store the images in your Google Drive or store the images on folders. You can upload it either way, and this should work. All right. Thank you so much for having me. We'll start with the series on NLP for the next two sessions. So what is natural language processing, how it works? Please do. Please feel free. So the next two sessions will be on natural language processing. That is going to logically conclude whatever topics the teachers have to teach to the students of 9th and 10th. And after that, if the audience requires, we can have customized sessions based on which specific topic you would like us to discuss. All right. Thank you so much for joining the session today.
Thank you once again, Dr. Gupta, for another informative session. We also thank the
you, Sneha.
participants, and I'm sure you must have been benefited a lot from today's session. There are more such sessions in store about which you'll be duly notified. Thank you. Have a great weekend ahead.